and efficient hardware implementation, because in millimeter wave the bandwidth is more, so your sampling frequency is also much lower, right? So we need fast samplers. That's not possible in your devices. So we are moving to that is the one band where we use communication. Anyway, I'll tell you that millimeter wave communication, how it is useful and how we do the beamforming in a separate slides. Now come back to the GFTM. I explained in a physical layer thing, the new waveform is GFTM. So this GFTM is already, I said, it's a non-orthogonal block-based multi-carrier technique. And actually it is covering OFDM and single carrier frequency division equalization as a special case. Okay. So how my GFDM is represented from OFDM? That's my understanding. So here the difference is the data source is same. Any mapper, maybe QAM, PAM or BPSK, QPSK, any mapper we use, that is also same. Instead of OFDM modulator, it is replaced with a GFDM. Here in the case, we also add cyclic prefix for the OFDM. In GFDM also we add some cyclic prefix, right? Then it goes through the wireless channel. We remove the cyclic prefix, we do some equalization, and channel estimation and synchronization are the most important issues in GFDM. And we go through the GFDM demodulator, then we use a detector, either matched filter, zero forcing or MMSC filter, and we do the demapping and we take data estimation. Okay, a typical block diagram of a GFDM modulator looks in this fashion. So what is new to us? The new is only a GFDM modulator. Okay, this new thing is GFDM modulator. So we try to understand how the GFDM modulator is constructed. So this GFDM modulator, so this GFDM modulator, if you look at the GFDM modulator, you can see that we can easily identify the difference from GFDM to OFDM. Okay, so what is the difference from GFDM to OFDM? Here in OFDM, we have blue color is a cyclic prefix, then followed by time samples. On each subcarrier, we are sending a cyclic prefix and data symbols. Okay, n time samples we are sending, n time samples and a cyclic prefix. Like that, on all the subcarriers, we are sending time samples and cyclic prefix. Okay, that we understood very well. Then coming to the frequency division multiplexing. So what is frequency division multiplexing? On each frequency, we send a different data, right? So along the vertical axis, if you look at along the vertical axis, we have a cyclic prefix in the blue color, and light blue, there is subcarriers. So in all these subcarriers, I am sending n symbols. So try to see this one. We are sending n symbols. Okay. So these n symbols are onto each subcarrier. And n frequency samples. Now how these two are merged together to go to GFDM, frequency division multiplexing, generalized frequency division multiplexing. If you look at this scenario, my n is actually k into m. So I'm using n time samples, right? Across all the n subcarriers, I'm using n time samples. That means on each subcarrier, I'm using capital N number of subcarriers, capital N number of time samples. So in GFDM, what we are doing, there are k number of subcarriers. If you look at the GFDM, k number of subcarriers along the vertical axis. Okay, the green color. The green is n is equal to your time samples. So these time samples are divided into k and capital M. That means k number of subcarriers, m number of subsymbols. Okay, so I take k time samples, not n time samples. I take k time samples and there are M subsymbols. There are M subsymbols. So these K time samples are actually located onto K subcarriers. K subcarriers. So these K subcarriers are actually given with only a green color with one, because it is a subset. Because if you look at this one, K equal to N into M, K into M, and K number of subcarriers, some number of frequency samples. So only one block consists of M frequency samples. Okay, there are K number of subsamples, and in this M frequency samples, the horizontally there are K time samples. So K time samples multiplied by M frequency samples will give you your total N. Both systems are carrying only N time samples. But how we are dividing? We are dividing in x-axis as well as in the y-axis. That is the difference in frequency division multiplexing. So pictorially we can see how it looks. What is the difference from OFDM to GFDM? So in OFDM, my data samples at the 0th instant. One time I started my transmitter. So at the 0th instant, I am observing 4 data samples. So for these 4 data samples, I have added a cyclic prefix, right? Because if you remember your diagram, at the end of your I50 block, there is an addition of a cyclic prefix. There is an addition of a cyclic prefix. Then at the next time interval, again 4 data samples, a cyclic prefix. Like that, as the data stream comes in, I take serial to parallel construction and I map accordingly. After mapping them, I port onto the endpoint FFT. Here in my case, maybe 4, n equal to capital N equal to 4 point FFT. So on to the top, after that 4 point FFT, I add additionally a cyclic prefix. Okay. Now GFDM. So what the GFDM is taking? At 0th time instant, I take 4 instances of my data. That is D0 to D1. At first instant, I take D0 to D3. At the second instant, I take D0 to D3. At third instant, like that, I take time slots. I divide it into time slots. On each time slot, the same data samples, but these time slots, they are generating different data symbols because at different time instances, the data symbols are also going to change, right? So all these data symbols are added with only one cyclic prefix. All these data symbols are added with only one cyclic prefix. Whereas in OFDM, after FFT block, we add a cyclic prefix. So as the data comes in, I add cyclic prefix. As the data comes in, I add cyclic prefix. Here for my entire time slots and for my subcarriers, I add only one time cyclic prefix. That means there is a huge saving of your bandwidth. Unnecessarily, we are allocating some amount of bandwidth to your cyclic prefix. That is one of the advantages in GFDM. So how it is executed, this GFDM? Just go through the block diagram. So this block diagram, maybe this is the total view of the block diagram. Okay, so I can show you the block by block. So if you look at this block diagram, there are actually the difference from GFDM to OFDM. You wait till n number of data samples, right? So these n number of data samples are ported onto your IFFT block. That means there involves only one capital N. But whereas in this case, I have to wait till n into m subsamples, because on each subcarrier, we are transmitting these data symbols using different modulo filters. Okay. So what is that modulo filter? Just look at this modulo filter. So I have raised D0, all D0 samples of m subsymbols, 0 to m minus 1 subsymbols are given, placed at different intervals, delta of n, delta of capital M minus 1 to n. They are located at different intervals. So these values, each sample is modulo operated by your filter, that is Gn of mod cap of Nm, Gn of mod cap of Nm. Then these M subsymbols are modulated onto a single carrier. That's the beauty of it. That is exp of 0. That means one carrier. The subcarrier is 0. So these 0 subcarrier data is given to your GFDM modulator. Summed up. Like I'll take next stream of Epsom symbols. We'll map the stream of Epsom symbols into a prototype filter and we'll port it onto the next subcarrier. So that means your understanding is on each subcarrier, there is a capital M number of subsymbols, right? Total, how many subsymbols you are transmitting? N into M, that is capital N into capital M number of subsymbols you are transmitting. At the end, we add a cyclic prefix. At the end, we add a cyclic prefix for your GFDM. That is the difference from GFDM to OFDM modulator. So we use different filter banks. And we use different filters, pulse shaping filters. So if you look at the pulse shaping filter time frequency response, for this one is for RRC filter. For different values of alphas in my RRC filter. Okay, sir. So we would see the power spectral density, how as alpha is increasing, the out of band leakage is also going to reduce. So this is the entire mathematical modeling of your GFDM model. So we take all these operations into consideration, like upsampling, the pulse shaping, and subcarrier upconversion into a single matrix notation, that is X equal to A into D. And how we design that X is known as a transmitter modulated matrix. And this in this transmitter modulated matrix is actually a NM cross M filter matrix containing the G's, as I said in the beginning. These are the G's, right? This is the G of N mod NM. Those G's of length NM and successive columns are shifted versions. And we take a diagonal matrix, is NM cross NM diagonal matrix. These diagonal elements are actually concatenated copies of the vector, that is e power j's. 1, e power j, 2 pi by n, and so on and so forth. And D is the vector of size. I said NM into 1 data blocks we are transmitting over 1 GFDM symbol. This is a stack of elements of all the vectors. So we concatenate all these values. It moves to X equal to A into D. This is the formula. And I receive this signal. That means R equal to HX plus W. H is my channel, X is the data, what I transmitted, W is the noise. So this H is actually the padded version of H, because we made N into M length. So your channel length also, if it is N into M, your decoding scheme will become very easy. So to be organized in such a way, it becomes N into M, and I receive the signal, that is FFT of R, FFT of H, then I compute the IFFT. So we can estimate your Ds using a normal receiver, a MMSE receiver, and zero forcing receiver. So these are the 3 different equations for my GFDM modulator. So, and also we derived a probability of error equation for the GFDM symbol error rate. We obtained this formula for probability of error. And also we have seen the noise enhancement factor for GFDM. And we compared the performance of a multi-tapper GFDM, which improving the orthogonality in GFDM. Okay. And also we have considered a multi-tapper GFDM. That means the filter bank is changed, and with a new filter bank, then we have seen the different structures of the outputs of the probability of error also computed. And we have seen what are the parameters we set for GFDM and GFDM DPSS. Also for GFDM and OFDM, the parameters are same. For GFDM GPSS, the parameters are slightly changed. that is the DPSS filter bank is used, and we have obtained different results for GFDM. So if you look at this GFDM taper, simulations and the original values are matching 1 to 1. Okay. So this is about a GFDM. So if you have any doubts, please ask me some questions on GFDM before, because it's already 4. So 1 more hour is left out. I can take to the new communication scheme.
Sure, ma'am. Ma'am, there is a question in chat box. Even in FBMC also, we use filter bank in 5C.
Okay.
Then GFDM is better or FBMC is better?
This is an entirely different structure, right? GFDM and FBMC are different structures. So I would say GFDM comparison with FBMC, GFDM gives much, because here the cyclic prefix is only at one time. So we are saving the bandwidth, and also it gives a better performance than the other one. The only thing is the complexity is increased, because we have to modulate those data into the prototype filter. Then after prototyping, we'll port that data onto the same carrier for M subsymbols. So similarly, if there are suppose n number of carriers, on each carrier 5 subsymbols are ported at a time. That is the main difference from GFDM to FBMC. Where FBMC is same as OFDM. Only thing is, at the end, to localize your frequency spectrum, we use a filter bank. But whereas in this case, it is entirely a different structure. Okay, so I cannot compare with the FBMC and GFDM, because the complexity wise GFDM is more complex. The FBMC is not that complex. Only the main difference from FBMC to the OFDM is we use a filter bank at the end.
Okay, ma'am.
So any other questions?
No more questions, ma'am. Participants, if anybody is having any queries, you may interact directly with them by unmute yourself.
Okay, just
hello, ma'am.
Yeah. Tell me.
This is Sarana Kumar calling from Madanapalli Institute of Technology.
Yeah.
May I know what is the next level of LTE, madam?
We are currently in LTE advanced, right?
Yes, we are in currently LTE, but not in the 4G. May I know what is the next level for LTE? So
the next level for LTE is 5G.
Madam, actually my friend is, actually this question I asked yesterday morning also, madam. My friend is working in Samsung Noida. He is working under the protocol of 6G. May I know what is the type of application is it better to use for 6G?
So for 6G, it is beyond 5G, right?
Yeah, now they are working, madam. Actually, the protocol is ready. My friend is making the white papers also.
Okay.
But he is not revealing because of the confidentiality of the company.
Yes.
Yeah, so may I know what is the advantages of 6G?
Even more, much faster. The latency is 1 millisecond. Less than 1 millisecond you are expecting in 5G. So in 6G, maybe 0 millisecond.
Ma'am, how this will be helpful for the IoT and artificial intelligence people's this communication?
Everything is again through research. So you generate papers, you simulate.
Any current research papers are available related to this, madam?
Which one? GFDMC?
It's about the 6G network.
Yes, you can see many papers in IEEE.
Okay, thank you, ma'am.
Yeah. So just a minute, I'm just charging my laptop. Okay. Okay. So now I start with another. So he is one participant is very curious about 6G, what 6G looks like, right? So maybe I can throw some light on 6G, how it works. So we are looking for new applications because there is a millimeter wave band is available, right? And even the lot of the spectrum is already overcrowded. So what next? How can I use my other applications into communication? So okay. This is one of the new area, the visible light communication. So as one person is asking me about what about 6C, what kind of applications you are going to use. So
Madam, yes, ma'am. I heard about this one also, madam. Li-Fi.
yeah.
We have Wi-Fi, we have Wi-Fi and Li-Fi.
Yes.
Yes, L-I-F-I. Yes, ma'am. I heard about this one.
Yeah.
Yeah, ma'am.
So I'll tell you in a simple way what is this visible light communication. Because everywhere when you are going, we need lot of bandwidth, right? The bandwidth is almost crowded. There is no space to give you personally to use for your applications because of many narrowband IoT devices are want to connect to the internet at the same instant of time. It is not possible. Then what is the other alternative? So other alternative is you have to search for new technology. You have to search for somehow I want to communicate my signal and I have to search for the frequency band. So there is a huge bandwidth is available in light. So this huge bandwidth available in the light, I can throw you some spectral analysis, spectral frequency components of my light wave. So if you look at this light, here, as we are increasing the frequency is like 10 to the power of 0 to that is long radio waves, then AM waves, so FM waves, right? Already these radio waves up to 10 to the power of 8, 10 to the power of 6 to 10 to the power of 8, the radio waves are already filled. Then we are into 10 to the power of 10, that is microwave. So in nanometers, it is 10 to the power of minus T. So this microwave is already filled because we are using for satellites, other microwave applications. Then infrared. So infrared is covered with your remote TV remotes. We are already using infrared band is also filled. Then what is the next band? The next band is visible light spectrum, right? This is the blue color, blue, red and green is a visible light spectrum. So this blue, green, red visible light spectrum, we have not used this one for communication. But rest of all already we have used for the communication. Infrared we are already using it. Microwave we are using it. FMAM we are using it. Long radio waves also we are using it. Then the next band is ultraviolet. Already we are using it for some health applications, X-rays, gamma rays, like that, right? So many rays are available. So everywhere the application exists. For in the ultraviolet rays, so in this band, there is in the visible spectrum, there is no application available. So this visible spectrum is actually working at 400 nanometers to 780 nanometers, 780 nanometers wavelength band. So that means in terahertz band. Okay. So this band we can use it for your communication purpose. That's what people thought of. And even in 5G, this is one of the application where a new application, because entirely a new communication, we want to start it. So this new communication is possible through your normal light emitting diodes and a photodiode. So what the light emitting diode does and what the photodiode does. So just I'll give a brief writing of your light emitting diode and a photodiode. Okay. So I have just I'm saying that I want to communicate because my communication is always in alternating currents, right? We do modulation, we do take digits, we do modulation, but ultimately when we are sending to through the antenna to transmit over the air, it must be a sinusoidal waveform. So I am taking the end sinusoidal waveform. So maybe my end sinusoidal waveform looks like one waveform. This is my waveform I want to transmit. So I am saying that devices. What are the devices? Light emitting diode. LED, we know very well what is LED, light emitting diode. And I know that a diode takes photodiode. So if light falls on it, it emits, when this emits light, this takes light. Okay. So here for emitting light and taking light, I want to use this LED and photodiode, PD, photodiodes. So when light emits from here and it falls here, so these changes, if I can observe through some circuitry over here, if I can send my information through this diode, my transmission is done. That means it is a wireless channel. This whole is wireless channel. Okay, at least for a long, at least for short distance communication in a building. Suppose so it is already overcrowded. Wi-Fi is already overcrowded. There is no space for the Wi-Fi. Any new mobile is entering into the hotel room, it cannot access the Wi-Fi because of the huge number of devices already connected to the Wi-Fi. Okay, then how to combat these problems in how do you manage your communication link? How do you do that communication? These are all important for us. So, okay, so then we know the fundamentals. What is the fundamental? LED can take only positive current. It cannot take a negative current. That means it allows the positive direction, but it won't allow the negative direction. It won't allow the negative direction. Right? But my communication is in sinusoidal format. My waveforms are in sinusoidal format. So how do you manage that one? At least not a sine. I am sending a rectangular pulse. So it will allow only positive, but it cannot allow negative. Then, so what is the other alternative? So somehow when I am passing the signal through LED, it is connected, a sine wave is connected through the LED through some biasing, right? It allows this current and this light falls on the LED. So that is photodiode. The photodiode will give you the output in the form of your half-wave rectified waveform. This is half-wave rectified waveform. This one is missing, right? Then you do lot of variations to your sign such that somehow my voice would reach to the photodiode. So one form of doing that one is you have a sine wave. I have a sine wave. So if you 0 is here, if you shift this 0 to down, then means the total thing is becoming positive. Then if the total signal is positive, the diode can allow this positive signal. Okay. So that means clipping, clamping. So I used a clamping to my signals so that it can forward through my diode. It falls on the photodiode. I can receive my signals. These are all so I can do some communication, right? So this way I can do my communication.
Ma'am, thank you, ma'am. I get your point, madam. Madam, I like to do research on this area. May I know which softwares, emulators or simulators are helpful for me to do the preliminary work?
So I'll share my screen because I'm already somehow. So what the work we have done at our laboratory, I'll share it with you.
Ma'am, in the meanwhile, I'm requesting the organizer, please give the recorded videos for us, madam, because this is very excellent session. So please give the recorded videos for us, madam.
I think they are already recording.
Yeah, recording is going on, madam, but I'm requesting the organizer to forward this one, madam.
Sure, sir, sure.
Forward it.
Thank you, madam. Thank you so much.
Okay. So this is the way, right? So this spectrum is available, and because my time is also going ahead, quickly I'll go through this comes under optical wireless communication, okay, because I'm using optical devices. So the name is also optical wireless communication. So this Wi-Fi modulation, if you are I can go with normal, all your communication streams can be directly adapted to your optical also. So when you are adapting to the optical, you have to bring some changes to your signals. That's it. If you can bring some changes to the signal, I can transmit my signal. But the length of your communication link is short. I cannot communicate more than a kilometer. Maybe I cannot communicate more than 1 kilometer as well, because it is only light, right? So when you are transmitting the light, the ambient light, that is your sunlight, also the present, that sunlight also falls on your photodiode, then how to take care. There are many issues are possible, many issues, challenging tasks are there in this optical wireless communication. So if you look at this diagram, you can see that the light wave modulation scheme. I can go for OFDM, I can go for other multi-carrier communications, I can go for color domain modulations also in visible light communication, like ACO OFDM, PAM DMT, UFDMT, OFDM, UFDM, ACO OFDM. There are many thousands of variants are already people are finding out. They are giving their research problems. They are publishing their papers. We too publish some papers in this. So we did some little work on this optical OFDM. So what we did in this optical OFDM is we take a source data, QAM modulator, and we did some subcarrier alignment. Then why do we need this subcarrier alignment? I will tell you. So what is the additional block? IFFT is there, QAM there, source is there, cyclic prefix is there. Only additional blocks are in this for optical OFDM is subcarrier alignment and unipolar conversion. So these are the new additions to this one. Similarly, in the receiver, we use subcarrier as extraction because assignment is done, extraction is done. Then unipolar is not required because it's already falls on the optical device. I take care for my unipolar output. So I'll call it as DCO OFDM. Okay, so this DCO OFDM, direct current optical. DCO means direct current optical OFDM. I'm using some technique because it is a multi-carrier communication. That is IFFT. IFFT I'm using it, right? So in this IFFT, suppose you give a signal to the IFFT block. I give a 1 and 0 or 2 ones, maybe 4 ones to 4 point IFFT. What is the output of my IFFT? 1, 1, 1, 1 I am giving as input to my IFFT block. What do you expect at the output of your IFFT? Some answers from some feedback from you, from the participants through chat box. Kiranmayi?
Yes, madam.
Is it connected to YouTube live?
Yes, ma'am. Yes, ma'am.
Yes, madam.
No, it's not correct.
No, ma'am. Okay.
Because ATAL is a program restricted to only the participants, not for the public.
No, ma'am. They have given instructions to upload in YouTube.
Maybe to. No, it's not correct.
Okay, ma'am. We stop that streaming.
Yeah, because it is a okay, no problem. But as of now, I'm seeing we are not connected to YouTube.
Okay, ma'am. No problem. We stop the streaming, but they have given an instruction to upload all the recording sessions in YouTube.
Okay, then why do we need parallelly conduct many ATAL programs? Right?
Okay, ma'am. We stop the recording.
They themselves are in confusion mode. So if you give YouTube link, tomorrow they'll see the same link. They don't come back to your program.
Okay, ma'am.
So right, so here unipolar conversion and subcarrier alignment we are doing it. So this unipolar conversion and subcarrier alignment, why do we need this one? So my question is, when I am passing my signal through IFFT block, the IFFT output is in complex domain, right? But whereas my optical device, as I said just now, the optical device is LED. So LED takes only positive signals. So for taking that positive signal, anyway, I am doing that unipolar conversion. But still, if it is in complex domain, to make it in the unipolar domain, And to connect it to the optical device, I have to follow some Hermitian symmetry procedure. So this Hermitian symmetry procedure is, I have my subcarriers x1, x2, x3. So suppose let's take 1, 2, 3, 4, 5, 6, 7, 8. 8 subcarriers are there. So how do you arrange your data onto these 8 subcarriers? So I arrange some DC values, that is direct current, DC values, because this elevates your negative values to a positive value. Okay, how much biasing is required. Then I'll give x1, x2 is my data as it is. And at the center, I keep 0. The next, I fix complex conjugates, x3, x2, and x1 complex conjugates. That means there are n number of subcarriers, but I'm using, frankly speaking, I'm using only n by 2 subcarriers. My actual data is only n by 2 subcarriers, not the full length I'm able to use. Why you are making this one? Because we are making this one because uh, to to do this procedure, subcarrier alignment and unipolar conversion, your signal formats. So, and as well, ACO OFDM is also, I'm using a Hermitian symmetry. The first, all middle carriers, like alternate carriers, we are making it as zeros. There are some advantages. And also, I am sending through a PAM DMT, that is pulse amplitude modulation, discrete multitone. So, zeros and middle zeros, the pulses P1, P2, P3. And again, in the reverse order, P3, P2, P1, we are sending this data information. So now I can show you the test bed, what we have developed at NIT Warangal. So we use the PAM modulator and upsampling. And actually what we have done is, we use the same test bed what we have used for our RF communication. That means the output is taken from USRP. That output is connected with, I already said, no, we have to bring it to the clamping level. That means if all the negative values, we have to bring it to the positive side. So that positive side is connected. That means through a bias value. Then we have designed a driver circuit to the LED to drive the current to the LED, then passed over the wireless channel. So we used a photodiode and some transimpedance amplifier. Again, we used a down conversion of the down converted signal is given, that signal is given to the USRP. And we have used proposed some timing estimation algorithm, because something new has to be added to this. So proposed a timing estimation to this, and we have done the rest of the procedure. Okay. So this you can see it in my test bed. Kiranmai, because when I'm viewing it on the other Mac, the one portion is given for the participants. Participants cannot view the full view. Can you make my screen as a full view?
It's already in full view, madam.
So you are viewing the full view, right?
Yes, madam.
Okay, okay. But in my Mac, I am seeing only half side participants, half side. Okay, no problem. Maybe I have opened my video. That's the reason.
No, madam. Here we are showing full view. Lab view and two PCs and setup, everything is in full view.
Okay, so this is our setup. So we took almost a year to establish, because I identified the diodes, bias, and photodiode, how to model this the whole system in lab view. It took a lot of time, and my students successfully, they have demonstrated visible light communication link. So, sir, if you have any questions, please, you can raise your hand.
Yes, madam. In chat box, one participant raised one question. What is the optical channel here in the test bed, madam? Is it free space or fiber?
It is free space.
Yes,
it is wireless communication, optical wireless communication. Only devices are optical, but the channel is same as your wireless channel, like your mobile channel.
Yes, madam. Fine.
So, any other questions?
No, ma'am.
Okay. So, this is the one of the.
No, ma'am. One question, ma'am. What about losses?
What about?
Losses.
What about losses? Yes. The same losses what you are observing in the wireless communication, also similar to your optical wireless communication, only the devices are changed, right? Your wireless communication, we use antennas. Here in place of antennas, a diode and a photodiode is used. That's only the difference from optical communication to the wireless communication.
Okay, ma'am. There are no more questions.
Okay. Right. So these are all the ESRP's image we procured from National Instruments. There are transmitter and receiver antennas. So we have removed these antennas, transmitter and receiver antennas. You can see in my test bed. Just what we have done, the diode output, that is, you can see a blue light, right? Blue light is throwing at the down after the bias T. So that output, the diode output is directly given to the transmitter ESRP through a wire. And from the reception, because we don't have any other choice to keep our photodiode at the ceiling, so we used a stand, photo stand, and on top of it, we place the photodiode to place into the line of sight. Even non-line of sight also, we have received the signals. So we placed onto the top of the photodiode. Then from that photodiode output is connected to the receiver USRP. You can see the wire from the receiver USRP. But the transmission path from the transmitter diode to the photodiode is wireless. There is no connection between them. So then this is given to the lab view, and so identified the reception. So we can see the reception, the hues, signal imparity, like actually exactly the transmitted waveform is at the PAM, but the reception waveform is because of additive white Gaussian noise and the channel, it is dispersed in nature. But we use a timing algorithm to decode our outputs. So in phase data of the received packet. So there is a delay in the reception. We identified how much delay is there. From there, we started our decoding. So here we used a blind timing synchronization algorithm. And this is a PAM DMT, pulse amplitude modulation on the x-axis. And also we have set up for multi-carrier DCO FDM communication using QPSK modulation format. So we could see the QPSK modulation format, DCO FDM at SNR of 20 dB. Some of the applications. Okay. So please ask me some questions so that it is open to. So what exactly we have done in this? I can show you some papers what we have published already in visible light communication.
And one more question, ma'am.
Yeah.
Is there any security issue to be dealt with VLC?
Yes. Yes. There are a lot of security issues are also we have to deal with the VLC, but we have not considered any securities, just we have established a communication link. Because a third party vendor is when you are transmitting, it goes to the correct decoding scheme and the correct user. That is also important, right? We have to embed some securities to your protocol. That is also a new a minor modification to your normal security. How do you implement security to your VLC? This is also another area where you can explore.
Okay, ma'am.
So, okay, so my student, she has done a lot of work in visible light communication. So she published a channel estimation in optical OFDM, and she also covered peak to average power ratio analysis in multi-carrier systems, performance analysis of not only IFFT and FFT block, we also use discrete cosine transforms, discrete sine transforms for your multi-carrier communication links. And so we use the spectrum. So just directly, I'm going through this multi-modulation techniques, what she has acquired, and Directly I'm going to the work. So this Hermitian symmetry, one of the technique. And we have a very good publications in IEEE sensor journals and photonics journal and optics letters and open source communications. So just I can show you. Okay, what I do, I can show you the papers what we have published instead of going to the whole of the analysis, because it all deals with mathematics. Okay, I'll go to that papers what we have published. Okay. So this is our current work. What we are doing, you can just search through your Google Scholar citations. So recently we have published one paper on implementation of linearly pulse-shaped generalized frequency division multiplexing for visible light communication systems. This is with the Journal of Communication Society. It's a very high impact factor journal. And one more paper we have published in DC. So the GFDM is applied to VLC. GFDM is a RF communication, right? So this RF communication is applied to VLC. And we got a very good paper, and also we have tested this GFDM on visible light communication test bed. And there is another paper in IEEE photonics letters, that is a blind timing synchronization algorithm for DCO OFDM VLC systems, and a new PAPR reduction techniques in DCO OFDM for visible light communication systems. These are all some of the works what we have done at NIT Warangal. GFDM we have also implemented in RF testbed and spectrally efficient PAM DMT for IMDD optical wireless communication systems. So you can see very good publications in some of the areas like so actually we have PAPR reduction schemes, right? They have proposed a new selective mapping scheme for visible light systems. And one of my students is tested with some energy signal for intensity modulation and direct detection systems, theory, simulations, and experiments, and closed form analysis of various diversity techniques. Like that, you can see many more papers from my Google Scholar citation. And nice papers on VLC. If you want to really understand what is VLC and how it works, you can see Shushila Wapangi's paper, a low PAPR, multi-carrier and multiple access schemes for VLC. It's easy to understand, very simple paper, normal basic mathematics. There is no hardness in the math. And also, the another paper is channel estimation in ACO OFDM employing different transforms. So instead of IFFT and DFFT, she used discrete sine transform, discrete cosine transform, how the waveform changes, what is the structure, how the structure is changed, is given in channel estimation in ACO OFDM employing different transform techniques. This is the paper. Okay. And also performance analysis of past optical OFDM for VLC, synchronization in visible light communication. So many more, like I'll tell you the whole one of the paper is actually a review paper of 70 pages. You can, the whole of your VLC can be understand from that paper. I'll tell you that paper. Oh, yes. There is one survey paper, Current Illumination and Communication, a survey on visible light communication. Just download this paper. And if you cannot download, I can share with Kiranmai madam. So you can share across all the students.
Sure, ma'am.
Okay. Even I can share it now itself.
Sure, ma'am.
Yeah, tell me your mail ID, ma'am.
K Babburu.
K.
K B A B B U.
K B A
B B U.
B B U
R U.
R U
@gmail.com.
Yeah.
Yes, ma'am. It's good.
Yeah.
Okay.
So just I'm sharing this paper. If it is, I think it can be downloaded. Okay?
Sure, ma'am.
Yeah. So you can refer these papers, and you can do some additions to these papers. You can start working on it because it is an easy area to understand, and then also simple mathematics. With normal mathematics, you can do some good work on visible light communication. So this is about visible light communication. So if you have any doubts, please ask me before I move to the OTFS. But OTFS we have not started any work because it is a students are already.
Ma'am, actually we have a lot of information needed from you, but already it's time up, ma'am. If you give us another session, means it's really wonderful for us, madam.
But already is
Actually, you said not a session; it's a complete course, like you said.
Okay. Okay.
So it's not a time for us to discuss because most of the people are in the time of period. If it's another, it's really helpful for us, madam.
Okay. So that I can
Thanks, ma'am.
explain point by point.
Yeah, welcome, ma'am. Thank you, ma'am.
Yeah.
Ma'am, there is one question, ma'am, and Hanumanta Rao sir asking. Ma'am, can you explain about OTFC, please?
Yeah. We are not working on OTFS, but I can take some slides from others. I can explain you what is happening in the OTFS. Okay. Maybe. These are not my slides. We have not prepared anything. So, okay, this is the one of the tutorial you also can download from the internet. Orthogonal time frequency modulation scheme by Chokkalingam sir. He is a professor at ISA Bangalore and other group. Viterbi, you know the Viterbi, right? Who designed the codes, Viterbi codes. So what they are saying is the OTFS modulation in the delayed Doppler domain. So you know what is delayed Doppler domain. So this delayed Doppler domain is high-speed communication, like in bullet train. Suppose when you are traveling in the bullet train, the channel is entirely different, not even normal channel. So normal channel, even when you are moving in the car, sometimes you lost your signals, right? Because of the speed. Your mobile is moving, that means your channel is also moving. So how to overcome these channels? Even when you are running also, I want to access my internet or I want to call my members. So they have identified this signaling in the delayed Doppler domain. This is similar to my GFDM model, but I am not exactly gone into the mathematics, what is happening in the OTFS. I've just gone through this only the slides. And so this is signaling architecture, and there is some compatibility with the OFDM architecture. So how do you do the signal detection and what is the channel estimation, and because for any communication, the channel estimation, signal detection, multi-user communication, some pre-coding, right? So here he started with convolution modulation OFDM subcarriers, and the OFDM system model we have already seen. So the received signal constraints, how they look, and high Dopplers in OFDM. So OFDM can take care of your high Dopplers? That is important. So come to this, what is this high Doppler, delayed Doppler channel? So the received signal, suppose the channel is constant over the one OFDM signal. So till now, our assumption of your GFDM or OFDM is for a symbol duration, the channel is constant. But when it comes to the high speed traveling, the channel is not constant for a symbol duration. Even for a symbol duration is 1 millisecond or 1 nanosecond itself, the channel is very dispersive. That means there is a Doppler effect is also happening. Why Doppler? Because you are moving and the channel is moving. And suppose the other mobile is also moving. If both are moving, there is always a Doppler possibility is there. So here we are accommodated this paths, gains for P multi-paths. So how they look like H0, H0, H1, H0, they are moving in this fashion, right? So this is actually a circulant matrix H. So this circulant matrix H in the permutation matrix, these notations is represented using F, D, F, S. That is your received signal is actually F into R. So a diagonal matrix is introduced over here. X is your transmitted signal. So this goes to a delayed Doppler format of your matrix. So the received signal R is equivalent to channel matrix multiplied by S. Okay. How the channel matrix looks like? It is in a delayed Doppler fashion. So this delayed Doppler fashion channel matrix goes to if you pass this kind of a channel matrix, it is not for a symbol duration, the channel is not constant. The channel is going in a dispersive nature. So then how to combat that problem? So there is an effect of high multiple Dopplers in OFDM because each carrier is having a different carrier frequency. There is an intersymbol interference, right? And multiple Dopplers will affect, so difficult to equalize as well. And the channel gains are not equal and the lowest gain decides. So each of the high Dopplers in OFDM we cannot combat. Okay, then what next? The next is orthogonal time frequency space modulation. So we have already said generalized GFDM, generalized frequency division multiplexing. Here they are saying that orthogonal time frequency space modulation. So they are also in GFDM and OFDM. In GFDM and OTFS, the difference is along the x-axis, along the y-axis, I am doing the modulation. So here also along the time axis, along the frequency, we are doing modulation. The structure-wise, both are same. Only the notations are different. And it combats the Doppler spread. It combats the Doppler effect. Okay. So, and it works well in delay Doppler domain rather than in time frequency domain. That is what they are claiming. So, in this representation of a linear time invariant wireless channel, if you take, so the time frequency response of the OFDM, generally what we do, this time frequency response of your channel, we are converting into a time variant impulse response and a Doppler invariant transfer response. Because in a high speed mobility, right, there is a Doppler and there is a time variation. So we are moving around in this nature. So actually what we are doing, this time frequency response of the channel after passing through your H of t comma V transformation. This transformation, it comes to a Doppler variant transformation from here. So from the time variant response is also coming to time frequency and delay Doppler response. So they use SFT, a transform technique. So I am not very much confident in this SFFT transform technique because I have to little spare my time to understand what is happening. Just I have gone through the overall idea what OTFS is. Okay, so this time invariant impulse response, because earlier my impulse response is G of t and S of t minus tau d tau, but this time G of t comma tau. That is a modification to your delay Doppler channel. So your delay Doppler channel is actually what is happening. H is actually earlier we used tau. Now it also involved with velocity H of t comma tau. So it has velocity, it has time delay, and your signal is transmitted with S of t minus t, and you are applying normal your FFT operation. So e power j 2 pi bt dt dv. So this is called delay Doppler channel. So delay Doppler spreading function. Into the Fourier transform time frequency channel, if you use in the frequency domain, both are equal. H of t comma f sf e power j 2 pi f. So this time frequency response, it has frequency response, it has a time response. So like this, the equations are going to change. So this pair of equations, they come in a 2D picture, wireless representations. If you take, they go in a picture way, and how the signal looks in the power levels, the time variant impulse response looks in high speed communication in this fashion in a three-dimensional plane, and also the channel in time frequency and delay Doppler frequency. So they use SFFT and ISFFT equations, that is channel in time frequency and delay Doppler domains. So this is the way the OTFS is different from your normal GFDM or the OFDM. So GFDM, OFDM, we have considered only H of t. Here we are considering H of t comma V. The channel is different. So we are changing this channel. Suppose we can isolate this channel H of t comma V as H of t into maybe some convolution into H of V. If you can isolate, if the Doppler is taken out, if you consider it as a H of t as it is, then I can decode my signal, no issue. But it is a combination of t and v. So we have to spend a lot of time on it to understand what is a OTFS is. Even frankly speaking, I also not gone deep into this subject because I learned through only basics. So we use some Heisenberg transform and Wigner transform to make this time frequency domain into a delayed Doppler domain. This time frequency domain into a delayed Doppler domain. Before and after that, we use different transforms. SFFT and ISFFT transforms we use. That's what the difference from. So you can understand what is, you can ask me what is ISFFT and SFFT, right? How it is different. So it is a two-dimensional transform, whereas your FFT and IFT are single-dimensional transform. So ISFFT transform and SFFT transform, space phosphorate transform, right? Space and Fourier, both are included in this. So if you look at the space and Fourier, there is a time, there is a frequency. So that is x comma k comma l, a double summation. E power j 2 pi and k by n is our previous equation. And is also added with ml by m. So one comes through the space, one comes through the time. So the space Fourier phosphorate transform, inverse phosphorate transform. They do some operations on this delayed Doppler domain. They make into a circular 2D circular deconvolution form, and they make the outputs. But it's a very good work. So people who wanted to do a lot of math, they can even jump into this OTFS. So any other doubts?
No doubts in chat box, ma'am.
Hello, madam.
Yeah.
Madam, now 5G technology, they are using optical network as a backend, then connecting with the Wi-Fi, WiMAX, LTE. So many channels interfering. How they are controlling means Wi-Fi is also used, WiMAX is also used along with the optical backend. That concept I am unable to understand how the channels are assigned to each users in the different zones.
You mean to say currently also we are in Wi-Fi, WiMAX and optical devices, right?
Yes, sir. Yes, madam.
So the same scenario will continue even for 5G also.
Oh, okay. Same channels are extended over there also.
Yes. And also we do some little measurements because we are also going through the millimeter wave band. So there they do some measurements on millimeter wave band, how the channel behaves.
Oh, okay, madam.
But in narrow band, channels almost we use the same models.
Okay, thank you, madam.
Any other doubts?
And one more question in chat box. Can you please give some sample MATLAB codes for GFDM?
Okay, I'll try to share.
Okay, ma'am. So
I'll try to share with you. You can share with your participants.
Okay, ma'am. Sure. Any more?
So don't try to get something from somebody. Instead, you can try on your own. You try to understand first the OFDM, then learn the concept of GFDM. If you understand how to build a OFDM in MATLAB, the GFDM is a minor modifications, right? From there, you can learn some more things. But if a ready-made code, if I give it to you, just you will run it and you don't understand what is happening inside.
Exactly, ma'am. Exactly.
Yeah.
So no more questions, ma'am, from participant side, I think. So now, thank you for your wonderful session, madam. We came to know the new technology GFDM and also VLC in detail, and it could orient the participants to do research in that area.
Yes.
Thank you, madam.
Okay.
And one more request, madam. Most of the participants are requesting the PPT. If you could send us, we will share it with the participants, ma'am.
No, don't ask any PPTs. Some unpublished work is also still present in that.
Okay, ma'am.
It's not possible.
Okay, ma'am, then. Okay, anyway, I will share that paper, ma'am.
Yeah.
Already shared with me.
Ask them to see my papers from the Google Scholar citation.
Okay,
they can see what exactly we are doing it, because whatever I demonstrated here, my test bed is also mentioned over there, and it is also description is given very nicely.
Okay, ma'am.
So people who wanted to do research in visible light communication, ask my students current illumination and communication paper.
Okay, ma'am. Sure.
It covers all the basics of visible light communication. We say almost 80 pages paper.
Okay. 80 pages review paper.
Review paper. 80
Sure,
or
ma'am.
70, I don't remember exactly, but it's a very lengthy paper.
Okay, ma'am. Sure, ma'am. Sure.
Yeah.
Thank you, ma'am.
Yeah.
Thank you, madam.
Thank you so much.
Dear participants, please note that tomorrow's session will start at 9:30 a.m. Okay, we have mentioned in the schedule at 10 o'clock, but sir wants to take at 9:30 a.m. So be in meeting before 9:30. Okay.
Yes, madam. Thank
So
you.
whatever information I am having with me, I will share it later. Okay, with the WhatsApp group. Okay.